My name is Farhan. I'm standing in front of the Green Library at Stanford University, which is truly an intellectual hub for science and innovation. Today I'll be discussing nanotechnology and underlying ideas behind nanotechnology. For the first segment of this video, I will talk about how light acts as a wave. This idea was an essential component of classical mechanics, a subfield of physics. Classical mechanics, which mostly applies to objects on a larger scale, had been around for hundreds of years. This explained the movement of large bodies like machinery, projectiles, and even planets and galaxies such as this one. In this demonstration, I will show how light acts as a wave in an experiment called the double slit experiment, in which quantum interference is observed. For these demonstrations, we have to understand light on the visible spectrum. On one side, we have violet light, which has the highest energy and shortest wavelength. Each color down the spectrum has less and less energy until we reach red, which has the least energy and the longest wavelength. The colors each have their respective wavelengths of frequency, which are inversely proportional. The equation that describes the relationship between wavelength and frequency for a color is C equals lambda nu, where C is the speed of light, lambda is the wavelength of the light, and nu is the frequency, or the number of cycles that pass per second. The double slit experiment involves a laser beam, a plate with two parallel slits, and an observing screen. The laser beam shoots light in a wave-like manner, so when light passes through the slits, some waves overlap, causing wave interference. When we look at the observing screen, we can see bright bands of light and darker bands of light absorbed due to the wave interference. If we make a copy of the screen, we can more directly see the different intensities of light present. We can even move around the slits to see how it affects where the bright and dark bands of light are observed. For the next part of this video, I will talk about how light acts as a particle. This property is described by quantum mechanics, a subfield of physics, and it is essential to nanotechnology and its applications. The discovery of light acting as a particle gave rise to quantum mechanics, and this monumental discovery changed physics forever. The experiment that demonstrated the particle-like properties of light is known as the photoelectric effect. This phenomenon simply could not be explained by classical mechanics. To understand it, we need a bit of a background. Max Planck first proposed that energy is quantized, which means that only certain energy levels can be emitted or absorbed by objects. From this idea, Einstein came up with a solution for the photoelectric effect, which became essential to early quantum theory. In this video, I will focus on the photoelectric effect and the different ways in which classical mechanics and quantum mechanics explain this phenomenon. The photoelectric effect involves a light source, a metal, and a detector. Light is shown upon the metal, which contains delocalized electrons, which are electrons that are free to move around. In classical mechanics, light is described as a wave with an even amount of energy distributed throughout. Physicists believe that even with a dim light, the waves would be absorbed, building enough energy until an electron is ejected. They also believe that a more intense light would knock off the electrons faster, resulting in a higher kinetic energy. However, both of these hypotheses were wrong. If the light shown on the metal was not above a certain frequency, the dimness of the light did not matter. In fact, a very intense light that is not at the right frequency or color will not emit electrons at all. However, if we move the slider above a certain frequency or wavelength, we can start to see electrons being emitted. Additionally, the intensity of light doesn't affect the kinetic energy, but the number of electrons being emitted. Also, the speed of the electrons being emitted is related to the frequency of the light being shown on the metal. If we increase the frequency even more, we can see the electrons being emitted even faster. How could this be? Quantum mechanics can explain this phenomenon. Albert Einstein, keeping in mind Max Planck's idea that energy is quantized, proposed that light can be thought of as photons, or energy packets. He used a Planck relation that describes the energy of individual photons. The formula is E equals h nu, where E stands for energy and nu is the frequency of the light. The energy of these photons is not dependent on the brightness, but on the frequency or color of the light. Therefore, no matter the dimness of the light, if the light was at the right frequency with enough energy, it would still be able to knock off electrons. From these demonstrations, we can observe how light can act as both a particle and a wave. This wave-particle duality is a principle essential to early quantum mechanics. Scientists continue to explore how matter acts on this smaller scale, giving rise to a new perspective on how our world operates. Eventually, with the knowledge derived from quantum mechanics, scientists began manipulating matter on the atomic and molecular level, which is now known as the field of nanotechnology. Nanotechnology has allowed us to make great leaps in terms of technological advancement and will continue to do so for the foreseeable future. Now the question is, what will this technological revolution have in store for us? My name is Farhan Azam, and thanks for watching.